What is a number? It seems like a simple question, but the answer is a sprawling adventure that spans the entirety of human history and the universe itself. In this episode of the Human Odyssey, we journey back to a time before counting, when the world was a chaotic, unquantified mystery. We'll follow the first spark of mathematical insight as our ancestors learned to track the cycles of the moon and the seasons. We'll witness the birth of zero, a revolutionary concept that changed everything. We'll sail with ancient Greeks as they uncover the timeless truths of geometry in the shapes of stars and shells. And we'll see how a simple sequence of numbers found in a rabbit breeding problem can unlock the patterns of spiraling galaxies and the petals of a flower. This isn't a story about formulas and equations. It is a story about us. It is a tale of curiosity, discovery, and the relentless human drive to find order in the chaos, revealing how a simple concept, the number, became the most powerful tool we have ever created. I'm Danny, and this is a new episode from the Human Odyssey, and today we're going to talk about the story of numbers. Welcome to a new episode from English Plus Podcast. It began with a whisper, a feeling before a thought, a rhythm before a word. Long before us, in the deep, untamed quiet of the world, there was a pulse, the steady beat of a heart in the chest of a sleeping animal, the silent, patient cycle of the moon, from a sliver of a bone-white light to a great, glowing pearl and back again. The sun rose and the sun fell. The seasons turned. Winter's stark emptiness gave way to the tentative green shoots of spring, which swelled into the lush abundance of summer, then faded into the fiery decay of autumn. This was the world's first arithmetic, the rhythm of one, then another, a pattern. But for the nascent consciousness of our earliest ancestors, this was just the way things were. There was no one, no two, no three. There was only a wolf, and then more wolves. There was a single fruit on a branch, or a cluster of them. The world was a place of things, not of quantities. The idea of a number, a concept so fundamental to our modern lives that we can scarcely imagine a world without it, had not yet been born. It slept, a ghost in the machine of the universe, waiting for a mind to notice it. Our story, the story of a number, doesn't start with a genius scribbling equations on a chalkboard. It starts with a bone. Imagine a woman, tens of thousands of years ago, huddled by a fire as the last light bleeds from the sky. Let's call her Mara. Outside her cave, the world is alive with unseen dangers. Her family is small, her existence precarious. But Mara has a mind that sees patterns. She has noticed the moon. She has seen how its shape changes with a reliable, comforting regularity. It is a companion in the lonely darkness. One night, she picks up a wolf's femur, long and smooth. Using a sharp piece of flint, she carves a single straight line into its surface. The next night, as the moon's sliver has grown slightly fatter, she carves another line beside it, and another the next night, and the next. She isn't counting. The word 29 doesn't exist. She is simply creating a one-to-one correspondence. One mark for one moon. She is tethering an observation of the world to a symbol. This bone, which archaeologists would one day call the Ishango bone or something like it, is the birth certificate of a number. It is the first tentative step towards abstract thought. Mara wasn't just seeing the moon. She was recording it. She was capturing its rhythm and holding it in her hand. She had separated the idea of a day from the day itself. The mark on the bone was a ghost, a memory, a placeholder for a moment in time. It was the first number. For thousands of years, this was enough. Tally marks on bones, knots in ropes, pebbles in a bag, These were tools for the concrete. How many sheep left in the pen? Make a pile of stones. How many returned? Match them one for one. It was a mathematics of the tangible, a way of keeping track of the world as it was. But humanity was stirring. We built villages, then towns, then cities. We planted fields of grain and needed to store the surplus. We needed to trade with our neighbors. The old ways were no longer sufficient. You couldn't build a pyramid with a bag of pebbles. You couldn't run an empire on tally marks. You needed a system. The revolution came in the Fertile Crescent between the Tigris and Euphrates rivers, under the baking sun of Mesopotamia. Here, the Sumerians, a people of astonishing ingenuity, were building the world's first civilization. They had a problem. Their society was becoming complex. They had taxes, trade, armies, and granaries. They needed to record transactions, measure land, and calculate fields. They needed a way to write down not just many, but how many. Their solution was breathtakingly elegant. They used the humble clay tablets from the riverbanks. With a stylus, they pressed marks into the wet clay. But instead of an endless series of tally marks, they invented symbols for groups. A small cone shape for 1, a small circle for 10, a large cone for 60, a large cone with a circle inside for 600. This was a quantum leap. They had invented the idea of a base system. Just as we group things in tens, the Sumerians often grouped in 60s, a system we have inherited in our measurement of time: 60 seconds in a minute, 60 minutes in an hour, and in the degrees of a circle. Now, a king could record the wealth of his entire kingdom on a few clay tablets. A merchant could track vast inventories. A number was no longer just a mark. It was a symbol with a value, part of a grand logical system. But even in this sophisticated world, a ghost was missing. An absence, a void. What if a column was empty? What if a farmer had no sheep? How do you write nothing? For centuries, they simply left a blank space. But this was clumsy, easily misread. The idea of a symbol for nothingness was a mental hurdle that seemed impossible to overcome. How can you make a something out of nothing? It felt like a philosophical paradox. The answer would come from the other side of the world, in the dense jungles and sprawling civilizations of ancient India. Here, mathematicians and mystics were obsessed with the concepts of the infinite and the void. In their philosophical and religious traditions, nothingness, sunya, was not an absence, but a potent creative force. It was the space between things that gave them meaning. Sometime around the 5th century AD, an unknown Indian genius did something revolutionary. They gave nothing a name. They drew a circle, a dot, a symbol to represent the void. They called it sunya. When the Arabs encountered this idea through trade and conquest, they were mesmerized. They translated sunya into their own word for empty, sifr. The word traveled through the trade routes into Europe, where Italian merchants morphed it into a zefiro, which was eventually shortened to the word we use today, zero. Zero was more than just a placeholder. It was a number in its own right. It was the boundary between the positive and the negative. It allowed for a positional number system, where the value of a digit depends on its place. The 1 in 10 is different from the 1 in 100. All because of the humble zero. Without zero, there is no algebra, no calculus, no computer science. The modern world is built on a foundation of nothing. The invention of zero was like discovering a new primary color, one that had been there all along but had remained invisible. It filled a void in the very language of the universe. As civilizations were mastering the art of counting things, another question began to haunt the curious. What about the space between things? What about the land itself? This question obsessed the ancient Egyptians. Their entire civilization was beholden by the Nile River. Every year, it would flood its banks, washing away the markers that delineated one farmer's field from another. When the waters receded, chaos ensued. Disputes over land were constant and violent. The pharaoh needed a way to restore order, to remeasure the land precisely. From this practical need, a new kind of mathematics was born. They called it geometry, which literally means earth measuring. The Egyptian surveyors, or rope stretchers, were masters of practical geometry. They knew that if you took a rope with 12 equally spaced knots and pegged it into the ground to form a triangle with sides of 3, 4, and 5 units, the corner opposite the longest side would be a perfect right angle. This was an incredibly useful trick for building the foundations of temples and pyramids with astonishing precision. They were discovering the rules that governed shapes. But for the Egyptians, these were rules of thumb, practical recipes for solving specific problems. They knew that it worked, but they didn't seem to ask why it worked. That question would be taken up by their neighbors across the Mediterranean Sea. The ancient Greeks were a different breed of thinkers. They weren't content with just practical knowledge. They wanted to understand the underlying principles, the timeless universal truths. They fell in love with geometry. For them, it was more than just measuring land, it was a window into the mind of God. A man named Pythagoras, who may have been one person or a whole brotherhood of mystics, became fascinated by the relationship between numbers and shapes. He and his followers believed that numbers were the fundamental building blocks of reality. All is number was their motto. They discovered that the harmonies in music correspond to simple numerical ratios. A string plucked in half produces an octave. A ratio of 2 to 3 produces a perfect fifth. The universe, they believed, was a grand symphony, a cosmos ordered by mathematical principles. Their most famous discovery, of course, was the Pythagorean theorem, the very same 3-4-5 triangle trick the Egyptian had used. But the Greeks weren't satisfied with knowing it worked, they wanted to prove it, to demonstrate with irrefutable logic that for any right-angled triangle, the square of the hypotenuse, which is the long side, is equal to the sum of the squares of the other two sides. This was a profound shift. Mathematics was no longer just about counting or measuring. It was about logic, proof, and abstract reasoning. It was about finding eternal truths that were independent of the messy physical world. A perfect circle or a perfect triangle doesn't exist in nature. There will always be imperfections, but they exist in the mind as pure ideas. The Greeks had discovered a new reality, a Platonic realm of perfect forms, accessible only through the power of reason. But this beautiful, orderly world was about to be shattered by a discovery that emerged from their own logic. The Pythagoreans believed that any length could be expressed as a ratio of whole numbers. They thought the universe was rational, tidy. Then one of them, legend says it was Hippasus of Metapontum, decided to apply their famous theorem to the simplest possible right-angled triangle, one with two sides of length 1. According to the theorem, the length of the hypotenuse would be the square root of 1 squared plus 1, which is the square root of 2. Hippasus tried to find a fraction, a ratio of whole numbers that would equal the square root of 2. He couldn't. And then, through a brilliant chain of logic, he proved that no such fraction could possibly exist. The square root of 2 was irrational. It was a number that went on forever, a decimal that never repeated, a ghost that could not be pinned down by the clean ratios of whole numbers. This discovery was a scandal. It was a crack in the perfect harmony of their universe. It suggested that there were numbers, and therefore realities, that were fundamentally unknowable, unmeasurable by their neat system. Legend has it that the Pythagoreans were so horrified by this discovery that they swore Hippasus to secrecy, and when he revealed it anyway, they took him out on a boat and drowned him. The story may be apocryphal, But it illustrates a profound truth. The world of numbers was far stranger and more mysterious than anyone had ever imagined. It contained infinities and paradoxes that would challenge the greatest minds for centuries to come. Now, while the Greeks were exploring the perfect world of shapes, another number was quietly revealing itself. Not in the straight lines of triangles, but in the gentle curve of the circle. The circle is the most perfect, most universal shape. It is the sun, the moon, the pupil of an eye. From the moment humans began to build, we have been fascinated by it. And one of the first things you notice about a circle is that there is a fixed relationship between its circumference, the distance around it, and its diameter, the distance across it. If you take any circle, no matter how big or small, from a wedding ring to a planet's orbit, and you measure its circumference and divide it by its diameter, you always get the same number. Always. This magical, constant number we now call pi. The Babylonians knew it was a little more than 3. The Egyptians used a value of about 3.16. The Bible, in its description of King Solomon's temple, implies a value of 3, but what was this number exactly? The challenge was taken up by one of the greatest minds in history, Archimedes of Syracuse. Archimedes was a force of nature, a man whose genius seemed to know no bounds. He was an engineer, an inventor, and a mathematician of the highest order. To calculate pi, he came up with a brilliantly simple idea. He couldn't measure the circumference of a circle directly, so he would trap it. He drew a hexagon inside a circle and another hexagon outside it. The circumference of the circle, he reasoned, must be somewhere between the perimeters of the two hexagons. Then he did it again, with a 12-sided polygon, and a 24-sided one, then a 48-sided one. The more sides he added, the closer the polygons hugged the circle, and the tighter the squeeze on the true value of pi. After calculating with a 96-sided polygon, a Herculean task without modern computers, he pinned pi down to an astonishingly accurate range, between 3.1408 and 3.1429. But Archimedes realized something profound. No matter how many sides his polygon had, it would never become a perfect circle. There would always be a tiny gap. He understood that he could get closer and closer to the true value of pi, but he could never reach it. Like the square root of 2, pi was irrational. Its decimal places march on into infinity, never repeating, never ending. This strange, elusive number pops up everywhere. It appears in the equations that describe the swing of a pendulum, the vibration of a guitar string, the colors of a rainbow, and the structure of DNA. It is woven into the fabric of the cosmos. The universe, it seems, has a fondness for circles, and wherever there is a circle, pi is there, a silent, infinite constant. For centuries, mathematics was largely a story of the practical and the philosophical. It was about counting goods, measuring land, and contemplating the ideal forms of geometry. But in the 17th century, a new kind of thinking began to emerge, one that would transform not just mathematics, but the world. It was the science of change. The world is not static. Everything is in motion. Planets orbit the sun. Apples fall from trees. Populations grow and shrink. How could you describe this constant flux with the static language of geometry and arithmetic? The challenge was taken up independently by two of the most formidable intellects of the age, Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany. They were both trying to solve the same fundamental problems. How do you calculate the speed of an object if its speed is constantly changing? How do you find the area of a curved, irregular shape? Their solution was one of the most profound and powerful inventions in the history of human thought. Calculus. The core idea behind calculus is to look at change in infinitesimally small steps. To understand the motion of a falling apple, Newton imagined breaking its journey down into an infinite number of tiny, frozen moments in time. In each of these instants, the apple has a specific velocity. By adding up or integrating all of these instants, he could describe the apple's entire journey with a single elegant equation. Calculus was the language of motion, of change, of dynamism. Suddenly, the universe, which had seemed so complex and unpredictable, began to look like a grand, intricate machine, a clockwork of celestial bodies all moving according to precise mathematical laws. With Newton's law of universal gravitation expressed in the language of calculus, you could predict the path of a cannonball, the tides of the ocean, and the orbits of the planets. It was a moment of breathtaking intellectual triumph. For the first time, it felt like we could read the universe's instruction manual. But even as calculus was explaining the grand motions of the heavens, a different kind of pattern was being explored. One found not in the stars, but in the humble world of plants and animals. In 1202, an Italian mathematician named Leonardo of Pisa, better known as Fibonacci, was pondering a curious little problem about the breeding of rabbits. Suppose you have a pair of rabbits. After 1 month, they mature. After a second month, they produce another pair. Each new pair follows the same pattern. How many pairs of rabbits will you have after a year? Fibonacci worked it out. You start with 1 pair. After a month, still 1 pair. The month after, they produce a new pair, so you have 2. The next month, the original pair produces again, giving you 3. The next month, the first 2 pairs both produce, giving you 5. The sequence of pairs goes 1, 1, 2, 3, 5, 8, 13, 21, 34, etc. Do you see the pattern? Each number is the sum of the 2 preceding ones. It's a simple recursive rule. But here is where the magic begins. This sequence, the Fibonacci sequence, seems to be a kind of secret code for growth in the natural world. Look at the petals on a flower. Lilies have 3 petals. Buttercups have 5. Delphiniums have 8. Marigolds have 13. Asters have 21. Not all flowers follow the rule, but a staggering number of them do. Look at the spirals on a pine cone, or the arrangement of seeds in a sunflower head. You will find 2 sets of spirals, one going clockwise, one counterclockwise. Count them. You will almost always find a pair of consecutive Fibonacci numbers like 34 and 55 or 55 and 89. The pattern is everywhere. In the branching of trees, the shape of Nautilus shell, the spiral arms of our own Milky Way galaxy. Why? Because it is the most efficient way to grow, to pack seeds, to arrange leaves to capture the most sunlight. It is nature's own optimization algorithm. A simple numerical pattern born from a thought experiment about rabbits turns out to be one of the fundamental blueprints of life. The story of a number is not a straight line. It is a branching, spiraling path, full of dead ends, paradoxes, and astonishing leaps of imagination. We discovered numbers that are negative, numbers that are imaginary, and infinities that are bigger than other infinities. We found that the solid, reliable logic of Euclides' geometry was not the only possible one. In the curved space of Einstein's relativity, parallel lines can meet. In the 20th century, our story took another turn, one that would bring us a full circle, back to the simple act of making a mark. We invented the computer. At its heart, a computer does not understand calculus or geometry. It only understands the simplest of all number systems, the binary code. It only knows 0 and 1, off and on. Every email you send, every movie you stream, every complex calculation that sends a rover to Mars is, at its most fundamental level, just a fantastically long string of ones and zeros. We have built a global civilization on the back of the 2 simplest ideas: something and nothing. From Mara's first scratch on a bone to the binary code that powers our world, the story of a number is the story of our own evolving consciousness. It is the story of our relentless quest to find pattern and meaning in a universe that can often seem chaotic and random. Numbers did not just allow us to count sheep or build pyramids. They gave us a language, a lens through which to see the hidden order of things. We look up at the night sky and see not just a random scattering of lights, but galaxies whose spirals follow the same mathematical rule as a seashell. We listen to a piece of music and hear not just a series of notes, but harmonies governed by simple whole number ratios. We look at our own DNA and find a complex code built on a system of repeating patterns. The universe, it turns out, has a voice. It speaks in the language of mathematics. The laws of physics are expressed as equations. The structure of reality is described by geometry. The patterns of life are encoded in numbers. So, was mathematics invented or discovered? It's the oldest question, and perhaps it is the wrong one. It feels like both. We invented the symbols, the system, the language. But the truths they describe, the fact that the angles of a triangle add up to 180 degrees, that pi is constant, that the Fibonacci sequence appears in a sunflower, feel like they were already there, waiting for us. They feel as real as mountains and rivers, timeless and universal. An alien civilization on the other side of the galaxy would surely have a different language and culture, but their value for pi would be the same. Their Pythagorean theorem would be identical. Our journey began with a simple tally, a way of connecting our minds to the world around us. It has taken us to the edges of the universe, the depths of the atom, and the core of life itself. The story of a number is not over. It continues with every new discovery, every new pattern we uncover. It is a story that is written into the fabric of reality, a story that whispers a profound and beautiful truth. We are not just living in the universe. We are a part of its symphony, and we are just beginning to learn how to hear the music. And with that, my friends, we come to the end of our episode, The Story of a Number, as part of our series, The Human Odyssey from English Plus Podcast. Thank you very much for listening, and don't forget to come back to listen to the rest of the series. I'll see you again next time.